Our Circuit Theory 2 course project. Our main objective of this project was to create a filter for vibrational frequency that we would then place on top of a DC motor of a drone of our choosing. Now, this filter is made up of an RLC bandpass filter that we learned about earlier this semester. This is only just one real world application that you can actually use an RLC bandpass filter, and you can even use this vibrational frequency filter for more than one application for quality assurance reasons. The drone that we decided to go with was the DJI Phantom 4 series. It has a general vibration frequency range of 95 hertz to 105 hertz on top of the DC motor. But this is assuming that it will be working at a constant output the entire time.
At first, we considered using an RC circuit that combines a high pass and low pass filter. However, it cannot create the resonance because it doesn't have the inductor and the Q factor cannot be adjusted. As a result, the peak response becomes flat instead of sharp. Therefore, we switched to using a RLC circuit like the one shown below. It has a clear resonance frequency as 1 over square root LC, and the Q factor can be controlled by using omega naught over bandwidth equation. This allows us to design a sharper and more tunable peak.
These were some of the formulas we used for our calculations. We chose the centered linear frequency to be 100 hertz and the capacitor's value to be 50 microfarads. We also chose the cutoff linear frequencies to be 95 and 105 hertz, and then calculated the angular cutoff frequencies as shown. Then calculated the centered angular frequency twice using two different methods. The method we used in our future calculations is highlighted in black. We used one of the formulas for centered angular frequency to solve for the value of the inductor, which was about 50 millihenries. Then calculated the bandwidth, which then allowed us to calculate the value of the resistor at 3.14 ohms. And then this was used to determine the Q factor, which is about 10, which is good for our application.
Here we wanted to start off with the transient state simulation to find our V outputs at the 95 hertz. Here we see we get 0.74 volts V output with the V input of 1, indicating that we're getting a high ratio showing that 95 is within our bandwidth for this filter. Moving on to the next slide, we see that at 105 hertz, which is our high end of our bandpass filter, we get 0.67 volts the output, and then we get a pretty high ratio as well. Here we wanted to use those values as we're going to see in the next slide, the center, the low end, and the high end of our bandwidth, and we wanted to see their gain at those frequencies. But we also did the calculations in the previous slide to prove that the transient states at those 95, 105, and 100 hertz show the same thing as the AC sweep. Here we wanted to go outside of our bandpass filter to see at what frequency we get 10 decibels of attenuation. And then we did that for the high end and the low end, which is shown here in both images. One more thing this slide covers is from the center to the low end and the high end, we wanted to see how much gain drop off we get. And so a 3 decibel drop from the center is good compared to after outside that region from 95 to 81, we get a 10 decibel drop off, indicating that the filter is working as designed.